In this video, we're going to look a little more closely at the stability of alkenes, and then we'll spend a few minutes looking at the elimination reactions of cyclohexanes. In class, we've already talked about the stability of alkenes and how monosubstituted alkenes are less stable than disubstituted alkenes, which are less stable than trisubstituted alkenes. But how did chemists figure this out? The easiest way to do that is to measure the heat of hydrogenation. This is the reaction that converts an alkene into an alkane. It's an exothermic reaction, and we can measure that heat to get an idea of the stability of alkenes. So if we look at these examples of alkenes, if we hydrogenate them, they all form the same alkane. And so the products of these three reactions have the same energy. And we're going to estimate that to be right there. But the starting materials don't necessarily have the same energy. And so if we look at a monosubstituted alkene, it undergoes a reaction coordinate diagram that looks something like that. And if we measure the heat of hydrogenation for this primary alkene, we get negative 30.3 kcals per mole. If we look at this disubstituted alkene, and measure that delta H, that delta H ends up being minus 28.5 kcals per mole. And if we look at this trisubstituted alkene, that delta H ends up being negative 26.9 kcals per mole. And so what we can see from here is that a monosubstituted alkene is roughly 2 kcals per mole less stable than a disubstituted alkene, which is roughly 1.5 kcals per mole less stable than a trisubstituted alkene. I want to switch gears a little bit and look at the elimination reactions of cyclohexanes. So below, hopefully you recognize this as an E1 reaction. And how do we know this is an E1? Well, isopropanol isn't a great nucleophile. It's a little bit bulky. It's a protic solvent, so I know it's going to go through a carbocation that's E1 or SN1. And the heat, or the delta symbol here, is telling me that it's going to favor elimination. And so I expect this to be an E1 reaction. And in the first step of an E1 reaction, the bromine just leaves, and we form a carbocation. That carbocation can relatively quickly rearrange from a secondary carbocation into a tertiary carbocation. Notice that when I do that hydride shift, I got rid of my stereochemistry because this carbocation is now sp2 hybridized, is trigonal and planar, and I have lost all information about the stereochemistry that the reactant had. From here, a molecule of isopropanol can pluck off a hydrogen and do an elimination to form this tri-substituted alkene. So that gets us to one product. The isopropanol could have come in at this carbocation and formed this alkene. In this product, the stereochemistry of the starting material is still there because I haven't rearranged the carbocation, and so I expect that methyl group to still be up. And in a final option, isopropanol could have picked up this hydrogen and done the elimination from here to form this product. And notice that these two products are the same molecule. I can form it two different ways. And it's a tri-substituted alkene, so these are the major product of this reaction. So E1 reactions are non-stereospecific or non-stereoselective, and they are going to form the most stable alkene or the most substituted alkene in most cases. Let's consider one that's a little bit harder. I want to look at the stereospecific elimination from cyclohexanes. So hopefully you recognize this reaction as an E2 reaction. I think this is probably E2. I've got a strong base. I'm a secondary alkyl halide. Maybe under these conditions, I could do some substitution with a non-bulky alkyl halide, but certainly if I heated this up, I would expect to favor elimination, or if I had switched this out for like a tert butoxide to be a very bulky base, that would be an E2 reaction and only an E2 reaction. And E2 reactions are stereospecific. So let's look at this. Cyclohexanes are special. Remember that in E2 reactions, the hydrogen departing must be anti-periplanar. With the leaving group. So in this case, my leaving group is bromine. In order to see anti-periplanar hydrogens, I really need to redraw this molecule in its chair conformations. The first thing I'm going to do is draw the most stable chair conformation of this molecule. So here we have the most stable conformation of this cyclohexane. Notice my Br is down, my methyl group is up. They're both axial. They're both equatorial. Because bromine is equatorial, there are no anti-periplanar hydrogens in this molecule. The hydrogen on this carbon is going down. That's gauche to the bromine. This carbon has 2 hydrogens. They're both also gauche to this bromine. If I draw the other chair conformation, my methyl group goes axial up. My bromine goes axial down. This hydrogen is now equatorial. There's a hydrogen that's axial up, and there's a hydrogen that is equatorial down on this carbon. This hydrogen is equatorial. It is not antiperiplanar to this bromine. The only hydrogen on this molecule that is both on the beta position, so that's 1 carbon away from where the bromine is, and antiperiplanar, both requirements of an E2, is this hydrogen. And so when sodium ethoxide comes in and deprotonates, this is the only hydrogen that can be removed. It must be that one. And we form an alkene here. If I redraw this in the stick structure, I've got an alkene, and this methyl group is still going up. So it looks something like that. Notice that this is not the most substituted alkene. This is the, in fact, least substituted alkene, but this is the only product observed in this reaction. Because of chair conformations, this hydrogen can never be antiperiplanar to this bromine. And so this is the only hydrogen that can be eliminated from this reaction. It's also important to note that the most stable chair conformation with bromine equatorial is entirely unreactive in an E2 elimination. The leaving group has to be in the axial position for an E2 reaction to take place. That's going to wrap up this video. We'll pick up with some more examples of E2 eliminations from cyclohexane in class next time.